I will be discussing the gamma function, which is sometimes called the factorial function, because it is in fact a generalization of the factorial that you use in higher mathematics. N factorial is just n times n minus 1 times n minus 2 all the way to 3, 2, and 1. So it's just a product of the first n integers. Well, what if n is not an integer? That's where the factorial function comes in. That's a generalization, and you can show that for this z can be any complex number, but for the specific case where z is n, you can show that this gives me n minus 1 factorial. So it's indeed a generalization of the factorial to any arbitrary value z, any complex number. Now, one of the great things about that is you also have a meaning for a negative factorial. So, by the way, this also tells me that I can write gamma of n factorial as gamma of n plus 1, because I just add, I advance it to the next step. So if I get gamma of n, if gamma of n is n minus 1 factorial, then gamma of n plus 1 must be n factorial. And that's where I generalize this to any argument. I say, all right, if n factorial is gamma of n plus 1, I'm going to declare that z factorial is, by definition, equal to gamma of z plus 1. So now I have the meaning for the factorial function for any complex number z, not just the integers n. So this is why it's called the generalization of the factorial function. In particular, you also have a meaning for negative factorial. So how cool is that? So for example, you have the one thing that we find when you do this is negative nu factorial. If nu is a positive number, then negative nu factorial has meaning as finite meaning only for non-integer nu. That does not belong to an integer. So that's one of the properties, because you'll find that negative n factorial for an integer is in fact plus or minus infinity. So depending on the value of n, you'll find that it's plus or minus infinity. So these are all some very fascinating properties of the gamma function that makes it a very useful function in any mathematical, advanced mathematical treatment of functions. So there is a identity. Gamma functions are not really useful in calculating integrals that much. That's where the beta function comes in. But gamma functions can be used in to reduce the complexity of a calculation. For example, let's find out what gamma of half is. Gamma of half is going to be the integral from 0 to infinity e to the minus t to the power half minus 1, which is negative half, dt. So you can actually change a variable here. So we can try changing variables to t equals t squared. So let's try changing the variable. T goes to, let's say, u squared instead of t squared. Then dt is going to be 2u du. Then this becomes, the limit remain the same. So e to the minus u squared. And then when I take t to u squared, I'm going to get u squared times negative half times dt, which is 2u du. Well, that's very nice, because u to the minus 1 times u is just 1. So I get 2 times the integral from 0 to infinity of e to the minus u squared du, which is just the Euler-Poisson integral. So that's 2 times the square root of pi divided by 2. So the 2's cancel out and I get root pi. That's a very useful result, that gamma of 1/2 is equal to root pi. And you can use that to reduce several interesting integrals to that form. The other really useful property for gamma functions is that gamma of x times gamma of 1 minus x is actually pi divided by sine pi z. Well, I wrote it in for x, so I'll just write it for x. It's valid for even complex numbers. So let me try to see that this is compatible with what we just found there. So let me put gamma equals x equals half. Then for x equals half, I'll get gamma of half times gamma of half, because 1 minus half is also half, is pi over sine of pi over 2, which is 1. So indeed I get gamma half squared equals pi, which means gamma of half is root pi. So it is compatible with the earlier result. And this useful identity can be used to relate gamma of x to gamma of 1 minus x, for example. So these are all extremely useful properties of this gamma function or factorial function. Like I said, it is most useful when we are interested in computing integrals from a more complicated perspective. So let's just try to find some values of gamma. Let's try gamma of something like 9/2. Well, first of all, gamma of 9/2 is not a standard value, so you have to do something to it to make it simpler. So the one thing I can do is use the result, which I have not written so far, and that is gamma of z plus 1 is equal to z gamma of z. This is sometimes called the reduction formula because it reduces the strength of the argument. You can see that the reduction formula automatically implies the result for n factorial, because if I keep reducing it, I'm going to eventually get n factorial or z factorial if it's thinking more generally. But for z equals an integer, let's see how this works. For z equals integer, I'm going to get gamma of n plus 1 equals n gamma of n, and that can be written as n times n minus 1 of gamma of n minus 1, and you keep going like this till you get to gamma of 0, because that's the last item you get. And gamma of 0, when you put 0 here, 0 factorial basically, actually you get gamma of 1, I think. When the last thing that ends up happening is you get gamma of 1, you don't go any further than that. And gamma of 1 is just 1 factorial, because that gives me gamma of 1 is 0 factorial, which is 1. So you end up getting the same answer, which is n factorial. So now let us go and calculate this using this result. So the first step is to write this as z plus 1. So let's do that. 9/2 is 7/2 plus 1. Well, that can be written as 7/2 gamma 7/2. Well, then I can write 7/2 gamma of 5/2 plus 1, which I can then simplify to 7/2 times 5/2 gamma 5/2. So you can see the order is reducing progressively, and so I get 7/2 times 5/2 And then one more application, gamma of 3 halves plus 1, and that you can use this reduction formula again. So it gives me 7 halves times 5 halves times 3 halves, and then I have gamma 3 halves, which, by the way, meanwhile I see all these odd numbers popping up in the numerator. 2 cubed, gamma of half plus 1, which is going to be 7 times 5 times 3 times 1 over 2 to the 4, gamma of half. And gamma of half, as we already showed, is root pi. So what I'm going to do here is just write this as, here's what I can do. I know that after 7 comes 6, so I'll do that, and at the same time I'll divide by 6. And after 5 I know comes 4, so I'll do that, and at the same time I'll divide by 4. And after 3 I know there's going to be 2, so I'll do that and multiply by 2. So that gives me 2 to the 5, because there's already 2 to the 4 down there, times root pi. Let's see if we can make this a little nicer looking. Upstairs is just 7 factorial, and downstairs is, I have a further 3 powers of 2. This is 3 times 2, so that's 1 power of 2, and that's 2 squared. So that's going to be 3 times 2 to the power 8 root pi. I don't think this is any better than writing just that, but it looks more compact.